Hello students, my name is Shashank Deep and I am Associate Professor at Department of Chemistry, IIT Delhi. Today I am going to talk about equilibrium. Generally, this is a very important topic in chemistry, since suppose we are taking a reaction, ammonia formation or PCl5 dissociation or any reaction which you can think of. We need to know that under what condition we can get maximum concentration of the product. So, in that case we will apply concept of equilibrium. So, in this chapter we are going to discuss about first what is equilibrium, when we can say that a reaction is in equilibrium, then we will look for the reason why equilibrium exists. Then we can discuss about type of equilibrium, and then we will discuss about homogeneous and heterogeneous equilibrium. What do we mean by homogeneous or heterogeneous equilibrium? Then we will discuss how to get equilibrium constant and what is the significance of this. So, we will calculate Kc, which is equilibrium constant, using equilibrium concentrations. Then we will also discuss the relationship between initial concentration and Kc value, types of equilibrium constant, relationship between Kc, Kp, Kx, a reaction quotient. So, we will calculate Kc if initial concentration is given. We can also go in an opposite direction. If Kc is given, we can calculate what can be the concentration at equilibrium. What is the concentration at equilibrium? So, let us first discuss about what is equilibrium, what do we mean by equilibrium? Equilibrium, what do we mean by equilibrium? For that I will use this picture. Equilibrium is basically a state of balance between opposite forces or action. A state of balance, you must remember this is called a state of balance, and there are two opposing forces. So, if we take a case of seesaw, here you see on the both side there is a person sitting, and so they are exerting force. So, this person exerting force in this direction and this person exerting force in this direction. They will get a balance only when the force is equal. Here balance between two opposing forces and we can get equilibrium. Suppose we have a reaction, we can take any reaction, for example A to B, A to B. Now, suppose I start with pure A. Suppose I start with pure A. So, there are suppose 6 molecules of A. If I leave A alone in a container, what will happen? That A will go to B. A to B is a spontaneous reaction, A is going to B. After some time, what we will see is the number of mole of A decreasing and number of mole of B increasing. So, suppose we have 4 molecule of A left and 2 molecule of B is formed. Now, suppose I look at the container after some time, I see more changes in the number of molecules of A and number of molecules of B. So, suppose now only 3 molecules of reactants is there and 3 molecules of B is formed. Now, again wait for some hour and then look at the container. Now, what I see is there is no more changes in A and no more changes in B. So, just look at, if suppose I give this state 1, state 2, state 3, state 4. So, we see that from 1 to 2 there is change in number of molecules of reactant and product. If I go from state 2 to state 3, again there is a change of your number of reactant and number of product. But after this we are seeing there is no change, there is no change. We can wait for more hour. If we do not see any change, that means equilibrium state is achieved. Equilibrium state is achieved. So, 3 and 4 gives you equilibrium state, equilibrium state. Now, take the reverse reaction B2A. What will happen? Again B2A is also spontaneous. So, what does that mean? Delta G for this process will be less than 0. So, suppose I start with B. So, only B molecules are in container and we leave it for some time. What I will see is B is going to A and suppose again 2 molecule of B goes to A. Now, leave for some more time, you will see that your more A is converting to B and we will go to the state where 3 molecules of B and 3 molecules of A is present, and then we will see no change. We will see no change, again 3 molecules of A and 3 molecules of B, as in case of your forward process. So, in reverse process we start with 6 molecule of B and then we see that again we are going and getting 3 molecules of A and 3 molecules of B. And if we leave it for more time, there is no change in the number of molecules of A and B, and then this state is called equilibrium state. So, suppose if I plot amount of A and B with extent of reaction, what you will see is there is a decrease of A, that is what we expect, and there is an increase of B with time, and finally, there will be a plateau and concentration of A. So, this is your A, this is your B. A decreases with time and there is a plateau. After that, concentration of A does not change, there is increase of B, and after some time there is no change in the concentration of B. So, concentration of A and B does not change with time at this plateau. at this plateau. And then we say that reaction has achieved equilibrium. On the other hand, if we start with B and look at extent of reaction and amount of A and B, then B will first decrease and then its concentration does not change after some time. A will increase and at this time the concentration of A will not change. So, after this time, when concentration of A and B are not changing, we say that equilibrium state is achieved. Equilibrium has been established. Okay, so now think of another reaction, A plus B giving you C. Again you will say same thing, initially A and B will decrease, A and B will decrease and C will increase. C will increase with time, And after some time, your concentration of A and B, A, B and C will not change. It means equilibrium state is achieved. So, when concentration of reactant or products are not changing with time, then we say that equilibrium state is achieved. Similarly, we can start from C. C will again go to A plus B. If we have only C in the container, it will go to A plus B till A, B and C does not change. When the change is 0 or there is no change happening, we say that equilibrium is achieved. So, what is importance of equilibrium? That in equilibrium all measurable properties of the system remain constant. And what is the balancing force here? Balancing force is rate of forward reaction. When rate of forward reaction becomes rate of reverse reaction or backward reaction, we say that equilibrium is achieved. Equilibrium is achieved. Equilibrium is achieved. Now, let us talk about why equilibrium happens. Reason for equilibrium. So, suppose we are talking about this reaction A gas to B gas. From thermodynamics, we know that this reaction is spontaneous only when delta G is less than 0. What does that mean? Gb is or less than G A. G B is less than G A. So, when G B is less than G A, reaction is spontaneous. Now, question is, if G B is less than G A, why reaction does not go to completion? The second question is, if G B is less than G A, why reverse reaction happens if we start from pure B? For this, let us again think about reaction A gas to B gas. So, we started from pure A and then we are going to pure B. In between, you have states where there is a mixture of A and B. So, sum of A exists as A and sum of A has gone to B. So, this is your first state, second state and this is third state. We know that free energy of this state is G A, this is G B, this is per mole of G free energy per mole of A, this is free energy per mole of B, and then you have G of the state 2. Now, how will we calculate G of state 2? Will be given by this. We can calculate by looking at this equation. So, suppose A gas going to B gas, we start with 1 mole, this is 0 mole, and at time t this is extent of reaction is E, then in that case left A is 1 minus E mole and this is E mole per liter. So, G of state 2 will be equal to G of this state 2 will be equal to 1 minus E multiplied by G of A. Since there are 1 minus E mole of A in the mixture, so we can just simply multiply G A by 1 minus E and plus. Now, in mixture we have E molecule of B, so we have E into G B. So, G 2 is equal to 1 minus E into G A plus E into G B. So, delta G for the process will be equal to delta G will be equal to 1 minus E G A plus E into G B, and since we started with 1 mole of A, so minus 1 into G A, and so this is G A minus E G A plus E G B minus G A. This G A cancels out. So, what we are left with is E G B minus G A, and we know that B is G B is less than G A. So, this is always going to be negative. So, what does that mean is, if we plot G versus extent of reaction, we will get equation like this, and that is quite clear from here that when we have E is equal to 0, then you are left with only G A. So, E is equal to 0 at this point, then your G is equal to G A. When E is equal to 1, this term goes to 0 and we have G 2 is equal to G B. G 2 is equal to G B. So, this is G A and G B, and if I just write down this G A minus E G A plus E G B. So, you can see that your G 2 is equal to simply G A plus E G B minus G A, G B minus G A. So, this is a equation of a straight line. If we plot G 2 versus E, slope will be G B minus G A and intercept will be G A. So, that is what you are getting here. So, slope is your G B minus G A, slope is your G B minus G A. So, what we expect is, since G B is equal to G B delta G is equal to negative at each point. So, what we expect that reaction should go to completion. However, we know that reaction does not go to completion. So, what is the things which stops reactions to go to completion? So, let us again think about the process. We started with pure A and we went to pure B. We went to pure B. Now, think of what is happening in this process. You start with pure A and you end with pure B. In between, there are states which are both A and B, which has both A and B. If these are separate, then the delta G which you calculated will be the way we got it. So, delta G will be equal to E G B minus G A. However, being in mixed state has contribution to entropy, So, mixed state always have higher entropy compared to the pure state. So, just if you look at the mixing process and try to understand about entropy, then in this first process where we are going from pure reactant to mixed state, delta S will be greater than 0. However, when we go from this state, state 2 to state 3, delta S is less than 0. This is just because of mixing. So, I am talking about effect of mixing, and this has contribution to delta G, and what we will write here is delta G mixture. Now, we know that delta G mixture, delta G is equal to delta H minus T delta S. If mixing is ideal, then we take this equal to 0. So, basically delta G mixing is equal to minus T delta S mixing. And we know that for first step, delta X mixing is greater than 0, and so this will be your delta G mixing will have your negative component. It will have negative component, but when you go from mixed state to pure B, delta S is less than 0, delta S is a negative quantity, and so this will have positive contribution. So, your delta G is, total delta G is, we know that this is your, this has negative contribution since G B is less than G A. Delta G mix has both type of contribution. If you take process this, it has a negative contribution. If you take this stage, it has positive contribution. When you are working with this state delta positive, there will be a time when this factor outweighs the negative part, and in that case delta G becomes positive. So, if we plot G versus E again, G versus E again, if you do not consider mixing, then you should get graph like this, but if we consider mixing, then there will be minus T delta S. Initially it will make the process more spontaneous, but after a certain time when delta G is greater than 0, you will get this kind of thing, this kind of state. And so, this is because of this change in entropy due to mixing that a reaction does not go to completion. A reaction does not go to completion. If there is no effect of mixing, then we should expect that delta G should be less than, always delta G should be less than 0. But it is because of mixing you have two different regime. In one regime delta G is less than 0, delta G is less than 0, and other regime delta J is greater than 0, and this is the point when delta G is equal to 0, and this is your equilibrium point. This is your equilibrium point. This is your equilibrium point. And again we can answer the second question also, that if we start from pure B, why reaction happens although G B is greater than G A. So, if there is no mixing, then reactions should not have happened, but due to mixing entropy increases, and that gives you negative contribution to G, and so reaction takes place. So, entropy of mixing is responsible for reaction not going to completion, reaction not going to completion. So, we discussed first about equilibrium. What is equilibrium? Suppose we start with A and just leave it in a container for some time. There will be a time when A and B, the concentration of A and B, ratio of concentration of A and B will become constant. A will not change, B will not change, and during that state no physical property will change. In that case, you tell okay, equilibrium is achieved. Reason for equilibrium is, although G of B may be less than G of A, when B is getting formed, A and B will mix, and there will be a time when this mixing will decrease delta G to such an extent that further conversion of A to B is not possible. Similarly, if we start from B, B will get converted into A. Since B is getting mixed with A, entropy of mixing is increasing. So, now we discussed about what is equilibrium and why that happens. Now, let us go and discuss about types of equilibrium. There are two types of equilibrium. One is your physical equilibrium and chemical equilibrium. Physical equilibrium and chemical equilibrium. So, physical equilibrium is when equilibrium is established in a physical process. While chemical equilibrium is when equilibrium is established in a chemical reaction. So, let us discuss first about what is a physical equilibrium. So, let us see, this is the condition which I am going to discuss is your melting of ice or freezing of water. So, freezing of water. So, this is the case when H2O liquid at 0 degree Celsius and 1 atmosphere converts to solid 0 degree Celsius at 1 atmosphere. Now, reverse process is melting when H2O solid at 0 degree Celsius and 1 atmosphere converts to H2O liquid at 0 degree Celsius and 1 atmosphere. So, you can think about this case. Suppose you take a beaker, you have water and then you put ice here. This is ice, okay, this is water, and if we put at 0 degree Celsius, then either water will go to ice or ice will melt depending on concentration of water and ice. So, at 0 degree Celsius and 1 atmosphere, your concentration of water divided by concentration of ice is going to be constant. Similarly, we can start from a ice cube and just leave it at 0 degree Celsius and 1 atmosphere. What you will see is that ice is getting converted into water. So, a small amount of ice will go to water. You can go in other way, start with water, put at 0 degree Celsius 1 atmosphere, you will see some freezing of water into ice. So, melting and freezing of ice or freezing of liquid water is a reversible process, and equilibrium exists between your water, ice and water liquid. Now, next thing you can think of is boiling of water molecule. Okay. So, suppose I take water and put at 100 degree Celsius, what will happen? That some molecule of water will get converted into water vapor. Not all molecule will go to your water vapor. Similarly, if I take water vapor and put at 100 degrees Celsius, it will sum of the amount of water vapor will go to water into the liquid form. So, an equilibrium is always established whether we start from liquid form or vapor form, an equilibrium will establish when there is no more conversion between liquid and vapor, no more conversion between liquid, and this is known as liquid vapor equilibrium. There are other cases of equilibrium, and for example, if you are looking at solubility of solute in solution. So, suppose I take water and I want to dissolve AgCl. You put some amount of AgCl, you mix it, you will see it will dissolve. But if you put extra amount, then you will see it is not getting dissolved. Only very small amount of AgCl goes into water. Okay. So, these are the soluble form Ag plus Cl minus, while you will see that lot of AgCl comes and settles down at the bottom. It means this is a reversible reaction, and Ag plus Cl minus is in equilibrium with AgCl solid form. AgCl solid form. Okay, AgCl solid form, and so this is a different kind of equilibria where we are looking at solubility of solute in solution. Now, chemical equilibrium. This is the till now we have discussed physical equilibrium. Now, we can discuss chemical equilibrium. Chemical equilibrium. You can take any chemical reaction A plus B going to C plus D. For example, formation of ammonia N2 plus 3H2 giving you 2NH3. You can look at dissociation of PCl5, PCl3 plus Cl2. These are the cases of chemical equilibrium. So, either we start with PCl5 or PCl3 or Cl2, there will be one point when reactant will stop getting converted into product. So, after a time, so 100% conversion is not possible, PCl5 does not goes completely into PCl3 and Cl2. Amount of PCl5 will change to PCl3 and Cl2. Now, equilibrium can be of different types. The type of equilibrium will also depend on phases, which kind of phases are there in the reaction. So, there are two different kind of reactions. First is your homogeneous reaction. In homogeneous reaction, all the components are in single phase. What I mean by single phase is it is either in solid form or liquid or gaseous form. All reactants and products. So, all reactants and all component means all reactants and products For example, if I take a reaction, now you can see that A in gaseous form is going to B in gaseous form plus C in gaseous form. So, all reactant and product A, B, C are in gaseous phase. This kind of reaction is called homogeneous reaction. Now, heterogeneous equilibria. Heterogeneous equilibrium. For example, if you take a solid, for example, calcium carbonate, this exists in solid form, and if we just dissociate it, it will give you calcium oxide solid plus CO2 gas. Now, you can see that although calcium carbonate and calcium oxide are in solid phase, your CO2 is not in solid phase. So, you have two phases in the reaction, solid and gaseous phase, and that kind of equilibria is known as heterogeneous equilibrium. Heterogeneous equilibrium. Now, what I told you about equilibrium is chemical equilibrium is the balancing force is rate of forward reaction and the other force is rate of reverse reaction. When they are equal, then we say that equilibrium exists. So, suppose I take a reaction A molecule of A reacting with B molecule of B to give you C molecule of C and D molecule of D. So, let us calculate what is the rate of forward reaction RF. We know that RF is equal to Kf, which is the rate constant, A power A, B power B. Similarly, we can calculate rate of backward reaction, and that is Kb C power C and D power D. Now, at equilibrium, since RF is equal to R reverse or R backward, so we can simply write Kf A power A B power B is equal to Kb C power C and D power D. In that case, we can simply write Kf by Kb is equal to C power C D power D divided by A power A and B power B. And since these are constant, Kf and Kb are constant, you can write K. And this K is called equilibrium constant. Equilibrium constant. So, you can see that if I use the condition Rf is equal to Rb, then we get this formula where C power C, D power D divided by A power A, B power B will give you a constant, and that constant is called equilibrium constant. And since here we are taking as concentration, this is also known as Kc. This is also known as Kc. So, suppose I take a reaction N2 plus 3H2 giving you NH3, 2NH3. Okay. So, in that case K will be Kc will be NH3 product, NH3 is the product. So, you see product square, since stoichiometry is 2 divided by N2, this comes from here, multiplied by S2, and since 3 molecules of S2 has been used, so put 3 here, and this is how we calculate equilibrium constant, NH3 square divided by N2 S2 3. So, we can calculate Kc using concentration of NH3 square N2 divided by N2 into S2Q. You must keep this thing in mind that this concentration is the concentration of ammonia at equilibrium, not at any time. This is the concentration of ammonia at equilibrium. Similarly, this is the concentration of nitrogen at equilibrium, this is the concentration of S2 at equilibrium. If you take some another point where equilibrium is not achieved, then the concentration ratio is not Kc. In that case, it is called Q, which is reaction quotient. So, this is different, this is not equal to Kc, and when we write this, this is NH3 at any time T square, this is not at equilibrium, divided by N2 at any time T where equilibrium is not achieved, divided by S2 but suppose this at this time equilibrium is achieved, it means the concentration of NH3 at that particular time is basically equilibrium concentration of ammonia. Similarly, N2 is equilibrium concentration of nitrogen, and S2 at time T is equilibrium concentration of hydrogen gas, then in that case Q becomes equal to Kc. Now, take this reaction again further, N2 plus 3 S2 is 2 NH3. Equilibrium can also be expressed in terms of partial pressure. Since all these 3 components, N2 is in gaseous form, S2 is in gaseous form, and NH3 is in gaseous form. In that case, equilibrium can also be expressed in terms of partial pressure of various gases. So, for example, in this reaction we can write K is equal to pressure of ammonia, partial pressure of ammonia square divided by partial pressure of N2 and partial pressure of S2 power Q, and that K is called Kp. This K is called Kp. So, this is different from Kc. In Kc we use concentration, whereas in Kp we use partial pressure. So, we can write, for example, suppose we take PCl5 giving you PCl3 plus Cl2, again these are in gaseous form. So, we can express this equilibrium in two different terms, Kc and Kp. Kc is basically PCl3 into Cl2 divided by PCl5, whereas Kp can be written as pressure of PCl3 into partial pressure of Cl2 divided by partial pressure of PCl5, partial pressure of PCl5. Now, once we know that what is Kp, Kc, we can also look at the relationship between this relationship. What is the relationship between Kp and Kc? So, let us think of same reaction PCl5 giving you PCl, PCl3 plus Cl2. These all are in gaseous form, and just I wrote down Kp is equal to pressure, or Kc is equal to concentration of PCl3 into Cl2 by PCl5. Suppose these are gases which follow your ideal gas equation. In that case, we can write simply PV is equal to nRT and P is equal to N by V RT. And we know that N by V is C, so we can simply write CRT. Okay. So, suppose I take Kp, Kp is P, PCl3 into PCl2 divided by P, PCl5. I can write this simply as P is equal to concentration of PCl3, concentration, then RT. So, multiply here by RT, and then Cl2, multiply this by RT, PCl5 divided by PCl5, multiply this by RT. 1 RT, RT cancels out. So, we can simply write that Kc into RT, Kc into RT, RT power 1. So, this is the way we can calculate the relationship between Kp and Kc. Let us take a general case, AA going to BB, plus BB giving you C molecule of C plus D molecule of D. In this case, your Kc will be, Kp will be given as pressure of C power C, pressure of D power D divided by pressure of A power A and pressure of P power B power B. And we know that P is equal to CRT. So, we can simply write C, this is the concentration of C, or let us write concentration of C into RT power C, concentration of D RT power D divided by concentration of A RT power A B RT power B. Now, we can simply write C into D, C power C into D power D divided by A power A B power B. Now, what is left is RT, and so we can just write RT C plus D minus A minus B, or we can simply write Kc into RT delta N. So, delta N is, where delta N is N of product minus N of reactant. So, for example, in this case you can see that N p is C plus D, whereas N r is A plus B. So, this is C plus D minus A minus B. So, there is a relation between K p and K c, and the relation is K p is equal to K c R t delta N, R c delta N. For example, if I take 2 NO, 2 gas to N2O4, N2O4 gas. Now, what is the relationship between Kp and Kc? So, Kp will be Kc RT delta N. You see N in product is 1 minus N in reactant is 2. So, it is simply Kc RT minus 1. So, this is the relationship between Kp and Kc for this reaction. Now, suppose we take another reaction, H2 plus I2, there again gas is formed, gives you 2HI, gas is formed. Now, in this case Kp is equal to Kc RT. Now, you see product is 2 minus 1 minus 1. That means this is simply 0. So, this is simply AP. So, for this reaction H2 plus I2 going to 2HI gas, your Kp is basically equal to Kc. So, till now we have discussed cases of homogeneous equilibrium. So, whether we take PCl5 going to PCl3 plus Cl2, N2 plus 3H2 going to ammonia, all components are in gaseous phase, and that is why we can say that these reactions are homogeneous reactions, and the equilibria established in these reactions are homogeneous equilibrium. Now, let us think about, if suppose I have a heterogeneous system, what will happen in heterogeneous? How will we express equilibrium constant in cases where system is not homogeneous, system is heterogeneous, there are more than one phases available. For example, calcium carbonate solid going to calcium oxide solid plus CO2 gas. Now, in this case we write Kc as simply concentration of CO2. Since concentration of solids are taken as 1, they are constant and taken as 1, and in that case Kc is equal to CO2, simply CO2. Or Kp, if I want to express Kp, I will just neglect the solid terms, I will simply write PCO2. So, Kp is pressure of CO2, Kp is pressure of CO2. We can again think of another equilibria like AgCl going to Ag plus Cl minus, Ag plus Cl minus. So, this is in solid form, and this is aqueous Ag plus, this is aqueous Cl minus. Now, again AgCl in solid form, and so we express Kc is equal to simply Ag plus into Cl minus. So, this is your K, and this is called solubility product Ksp. This equilibrium constant is called Ksp, and this is equal to Ag plus into Cl minus. So, today I will stop here. In the next class we will do more questions and discuss what is the effect of temperature pressure on the equilibrium constant.